Good morning, everyone, and welcome to our live coverage of another Rocket Lab Electron mission from Rocket Lab Launch Complex 1, Mahia, New Zealand. Today, we are on the brink of witnessing another monumental event in the realm of space exploration, as Rocket Lab is all set to propel their Owl for One for Owl mission into the space. We are awaiting for the 51st Electron liftoff at 4:39 a.m. New Zealand Standard Time, which will be 4:39 p.m. UTC for Japanese Earth Observation Company Synaptics launch on a mission named Owl for One for Owl. Today's mission will be the fifth launch of a total of 16 launches on Electron for Synspective. Rocket Lab's first launch for the company was in December 2020. Previously, Rocket have supported Synspective with launches named The Owl's Night Begins, launched on 15 December 2020. Next, The Owl's Night Continues, launched on 28 February 2022, followed by The Owl Spreads Its Wings, launched on 15 September 2022, and the last mission they launched for Synspective was All Night Long, launched on 4th March 2024. Now we are awaiting for the fifth launch. Today's mission will launch single new StriX small satellite, also known as StriX 5, for Synspective's constellation of Synthetic Aperture Radar, which is acronymed as SAR satellites, designed to deliver imagery that can detect millimeter level changes to the Earth's surface from space. This will be deployed in a sun synchronous orbit. This launch marks Rocket Lab's amazing 51st overall launch and 9th mission of this year. With the previous mission, Electron reached its 50th launch faster than any commercially developed rocket in history, breaking the record previously held by SpaceX Falcon 9. Hello, my name is Dipta Maitra, performing the commentary for today's mission launch. We are super excited bringing you the coverage of Rocket Lab's Owl for One for Owl mission, dedicated mission launch for Synspective's constellation of Synthetic Aperture Radar, and the mission is the fourth of 5 dedicated launches for Synspective's StriX constellation. Now let's get back into the today's mission Details. So far, Rocket Lab reports that the weather is looking promising for today's Electron launch opportunity and the range is ready to support. We hope that they are able to launch on time and not have to push off too far. Although this mission has a 14-day launch window that opened on July 30th. Rocket Lab is currently targeting a liftoff time of the Electron from Mahia, New Zealand at 4:39 am New Zealand Standard Time on August 3rd, which will be 4:39 pm UTC on 2nd August. Before moving on, firstly we want to express our heartfelt gratitude to everyone for joining us for today's launch. Also would like to welcome one of our moderator here, confession at 3 am, waiting from long time. And also right now Marcus Antonio has joined us. Welcome Marcos. Hope you guys will enjoy the stream. And we are truly delighted and appreciative of your presence here. A big shout out to our awesome and incredible YouTube community for tuning in as we offer detailed coverage of space launches, complete with extensive statistics and thorough insights. We really appreciate you being here. Now let's learn about our very own Electron in detail. Electron that's supporting today's mission is an orbital class reusable two-stage rocket which is 18 meters tall and 1.2 meters wide. An orbital launch vehicle designed specifically to place small satellites of up to 300 kilograms or 660 pounds into a wide range of low Earth orbits. Every aspect of Electron has been designed for frequency and reliability to meet the evolving needs of government and commercial small satellite operators. Electron's payload fairing protects the payload from encapsulation through flight, and the fairing is 2.5 meters tall and 1.2 meters wide. The fairing separation occurs using the pneumatic unlocking using springs. It can deliver 200 kilograms to 550 kilo. It can deliver 200 kilograms to 550 kilometers on sun-synchronous orbit. Electron's payload fairing is a composite split clamshell design and includes environmental control for the payload. During separation, each half of the fairing is designed to rotate on a hinge away from the payload, resulting in a safe separation motion. Expanded and tailored fairing options are also available depending on customers' need. Now moving on, Rocket Lab's Kick Stage, which offers customers unmatched flexibility for orbital deployment. The Kick Stage is a third stage of the Electron launch vehicle used to circularize and raise orbits to deploy payloads to unique and precise orbital destinations. The Kick Stage is powered by Rocket Lab's in-house designed and built Curie engine. In its simplest form, the kick stage serves as in-space propulsion to deploy payloads to orbit. Its most advanced configuration, the kick stage becomes Photon, rocketlab satellite bus that supports several year duration missions to low Earth orbit, mid-Earth orbit, lunar and interplanetary destinations. The Rocket Lab's kick stage is designed to deliver small satellites to precise and unique orbits, whether flying as dedicated or rideshare on Electron. The kick stage is streamlined path to orbit that eliminates the added risk, complexity and cost of having to develop own spacecraft propulsion or using a third-party space tug to deliver spacecraft to the desired orbit when flying as a rideshare. For missions that require extended payload support on orbit, or for missions exceeding 200 kilometers to middle Earth orbit, lunar or interplanetary destinations, Rocket Lab offers the Photon spacecraft bus, a high-performance evolution of the kick stage. Let's take a closer look at Rocket Lab's kick stage, a marvel of modern aerospace engineering. The journey begins with the kick stage separating from second stage, a critical maneuver that sets the stage for what's to come. Imagine the precision required as the kick stage engine ignites, circularizing the orbit. With the orbit circularized, we are at a pivotal juncture in the mission. It's a moment of perfect alignment where the satellites are poised for their grand entrance into space. Then comes the payload separation, a thrilling instant where the satellites are released to their desired orbits. But the mission doesn't end there. In a responsible twist, the kick stage performs a final engine burn to lower its altitude, gracefully bowing out of orbit. This not only marks the successful end of the mission but also showcases Rocket Lab's commitment to space sustainability. Traditional methods of deploying satellites can leave large rocket stages in orbit, contributing to the global issue of space debris. The kick stage has been designed with the capability to deorbit itself on an accelerated time scale, well before the 25-year deorbit guidelines stipulated by NASA. By performing a deorbit burn with the Curie engine, Rocket Lab can lower the kick stage perigee to increase aerodynamic drag on the spacecraft and cause it to deorbit within months or single-digit years as required. Again, we would like to thank all of you joining us for today's launch. And we are truly grateful to you, and we are really glad to have your presence over here. Now moving on, we have Electron's second stage. The Electron's second stage consists of a single vacuum optimized Rutherford engine and linerless common bulkhead tanks for LOX and kerosene. With an expanded nozzle, Electron's second stage engine produces a thrust of 5,800 pounds of force and has a specific impulse of 343 seconds. The 1.2 meter diameter second stage has approximately 2000 kilograms of propellant on board. The Electron stage 2 has a burn time of approximately 5 times with a Rutherford vacuum engine as it places the kick stage into orbit. High voltage batteries provides power to the LOX, that is the liquid oxygen, and kerosene pumps for the high pressure combustion, while a pressurant system is used to provide enough pump inlet pressure to safely operate. During the second stage burn, two high voltage batteries power the electric pumps until depletion, when a third high voltage battery takes over for the remainder of the second stage burn. Upon depletion, the first two high voltage batteries are jettisoned from Electron to reduce mass and increase performance in flight. The engine thrust is directed with electromechanical thrust vector actuators in two axes. Roll control is provided via a cold gas reaction control system, that is the RCS. And finally, we have the Electron's first stage, which consists of 9 sea-level Rutherford engines, linear less common bulkhead tanks for liquid oxygen, and rocket-grade kerosene, that is the RP1 propellant, and an interstage RocketLab's flagship engine, the 5,600 pounds of force. Rutherford is an electric pumped LOX, that is a liquid oxygen or kerosene engine specifically designed for the Electron launch vehicle. Rutherford adopts an entirely new electric propulsion cycle, making use of brushless DC electric motors and high performance lithium polymer batteries to drive its propellant pumps. This cuts down on much of the complex turbo machinery typically required for gas generator cycle engines, meaning that the Rutherford is simpler to build than a traditional engine but can achieve 90% efficiency. Rutherford is also the first oxygen or hydrocarbon engine to use additive manufacturing for all primary components, including the regeneratively cooled thrust chamber, injector pumps, and main propellant valves. The stage 1 and stage 2 Rutherford engines are identical, with the exception of a larger expansion ratio nozzle for stage 2 for improved performance in near vacuum condition. This is just the same as we have the case in Falcon 9. They are also the Merlin 1D engine. They have only this difference. Now all aspects of the Rutherford engines are completely designed in-house and are manufactured directly at Long Beach headquarters in California, USA. Now let's unpack some key features and milestones of this incredible spacecraft in a pictorial form. Here is a quick overview of Electron. Moving on, let's have a look at the payload details for today's mission. Today's mission, named Owl for one for Owl, is the fifth dedicated mission for Synspective out of 16 planned upcoming launches. This mission is a dedicated launch for small synthetic aperture radar satellites by Synspective, which is jointly developed by Synspective, University of Tokyo, Tokyo Institute of Technology, and JAXA. Today's launch is the fifth launch of StriX satellite for its constellation of Synthetic Aperture Radar. Also, as mentioned before, this is the fifth launch of a total of 16 launches on Electron for Synspective. Synspective's StriX satellites is in the 100 kilogram class and is about 1/10 of a conventional large synthetic aperture radar satellite, which utilizes a foldable antenna design which expands to a size equivalent to a 5-meter large satellite. It consists of a deployable parallel plate slot array antennas as well, equipped with a high output 1 kilowatt amplifier. It also features a balanced thermal control system. Its quality and stability reduces the potential orbital failures, making it advantageous for stable production and operation. Now, wide area imaging capacities are crucial for routing, monitoring, and observations during disasters. With synthetic aperture radar satellite system, power generation and storage capacity limits the area of observation. But with the StriX satellites, this is not the case, as because it is equipped with an high output 1 kilowatt amplifier and have many solar cells and a corresponding high capacity battery. As a result, the observation width per scan is 5 to 6 times more expansive, leading to an observable area that is 2 to 10 times larger than other satellites. This feature enables long-term and multi-point observations as well. Today's payload will be deployed in a sun-synchronous orbit of 543 kilometers with an inclination of 43 degrees. Now, today's fifth satellite performs better than its previous satellites and will operate in an inclined orbit. And this new satellite will enable Synspective to capture high resolution images of densely populated area in high demand low to mid latitude regions. Previously, with the previous StriX satellites, the satellite's imaging direction was limited to a single direction, resulting in an invisible area caused by the relationship between the satellite's imaging direction and angle and the slope of the land area. However, combining the satellites in an inclined and sun-synchronous orbit will enable observation from four directions, that is east, west, north and south, allowing Synspective to receive clearer image. Synspective's this new fifth StriX satellites use cases includes detecting anomalies in road, rail, energy and other infrastructure, resulting in low maintenance costs and accident and risk as well. Monitoring crop growth conditions and analyzing soil and vegetation's health to help reduce cost and increase efficiency for farmers. Detecting illegal logging and fishing in the most remote parts of the world. Providing rapid damage assessment after flooding, landslides and volcanic eruptions, as well as risk assessment for land subsidence. This will also enable the persistent monitoring of maritime traffic, border activities and other potential security threats, and advances maritime domain awareness. Also, another use case will be analyzing tree cover to calculate the carbon dioxide absorption and carbon credits as well. As mentioned before, with the help of the StriX constellation, we can get an millimeter level changes to the Earth's surface from space. Now let's have a look at the bar graphs with number of Electron launches each year. Before today's launch, rocketlab completed 8 launches of Electron so far this year as part of its milestone. With the recent No Time to Lose mission launch back on June 19th. That was rocketlab's 50th mission overall. This year's count already surpasses the total number of Electron launches from all the years leading up to 2021, and they are now getting equal to the number of launches made in 2022, with only one launch to go. That's going to happen in some minutes away. Now with today's mission launch, the bar graph depicts 9 Electron launches so far this year. That's just one less than the number of launches last year. Moving on, let's take a look into the flight profile for today's mission, which is somewhat distinct from other regular Electron launches, as Rocket Lab will perform an advanced mid-mission maneuver with Electron's kickstage to shield the satellite from the sun and reduce radiation exposure. Starting with the liftoff at T0, just 55 seconds into the flight, the vehicle goes supersonic. At T plus 1 minute and 6 seconds, the rocket reaches max Q, the point of maximum aerodynamic pressure. Then there will be couple of different events in rapid succession. At T plus 2 minutes and 37 seconds, we experience main engine cutoff, that is MECO on Electron's first stage. Just 3 seconds later, at T plus 2 minutes and 40 seconds, stage 1 separates from stage 2. Again 3 seconds later, at T plus 2 minutes and 43 seconds, the Rutherford engine on Electron stage 2 ignites. Then at T plus 3 minutes and 24 seconds, the fairing separation occurs. At T plus 6 minutes and 33 seconds, we will have the battery hot swap. Next up, at T plus 9 minutes and 3 seconds, we have second engine cutoff, that is SECO on stage 2. 4 seconds later, at T plus 9 minutes and 7 seconds, stage 2 separates from the kick stage. As we near the end of the first phase of the mission at T plus 54 minutes and 7 seconds, the kick stage Curie engine ignites, first time in today's flight. This Curie engine burn will last for approximately 2 minutes and 15 seconds. Shortly after, at T plus 57 minutes and 12 seconds, we have the payload deployment completion for the StriX satellite. As we are nearing to the webcast to begin, let's quickly have a look into the mission stats for today. This marks the 51st overall launch for Rocket Lab, showcasing their consistent excellence in the field. It's the 5th Synspective satellite launch out of 16 planned launches for their constellation of Synthetic Aperture Radar. Moving on to the launch frequency, this launch marks the 51st Electron launch to date, a testament to Rocket Lab's rapid advancement in technology and dedication to exploration. Also, this will be the 46th Rocket Lab's orbital launch to date. With this launch, we will witness an impressive 9th Electron launch and Rocket Lab's overall launch this year. Speaking of launch site achievements, this will be the 21st orbital launch from Pad B of Launch Complex 1 from Mahia, New Zealand. Also, this will be the 47th overall orbital launch to date from Rocket Lab's Launch Complex 1, which is a milestone that speaks volumes about the reliability and capability of the launch facilities. And let's not forget, there will be no first stage booster recovery planned for this mission, a strategic decision based on mission requirements. Now, if you feel that we are enhancing your viewing experience and somewhat adding any merit to the stream, please consider liking this video. It helps YouTube's algorithm attract more space enthusiasts to discover this stream. Also think about subscribing to us as we work hard to provide streams filled with stats and details, and doing so will really inspire us to work more hard, and we would be incredibly grateful for your support. Now moving on, let me walk you through the impressive overall Rocket Lab's stats that underscored this launch. With the Owl for One for Owl mission, Rocket Labs marks its 51st Rocket Labs overall launch and Electron launch to date, a testament to their relentless pursuit of excellence and innovation. This launch is not just a number, it's a milestone that reflects the hard work and dedication of countless individuals as well. As we dive deep into the numbers, it's heartening to see 46 orbital launches and 1 suborbital launch success to date. Each successful mission is a beacon of hope. Yet the journey of Rocket Lab is not without its challenges. Rocket Lab has faced 4 orbital launch failures to date. But these setbacks are not defects. They are lessons that pave the way for future triumphs. Rocket Labs has achieved 7 ocean recovery successes for the first stage booster to date, showcasing their commitment to reusability and sustainability. Adding to their list of achievements, Rocket Lab has successfully conducted 2 aerial capture tests of the first stage booster with recovery helicopters. This innovative approach to recovery is a glimpse into the future of spaceflight. Also, 2 successful controlled atmospheric re-entry tests were conducted to date. And not to forget, the 39 non-recovery of the first stage booster instances, which includes today's launch. With this launch, it will be 191 satellites launched by Electron, 509 Rutherford engines sent to space. As we know, each Electron launch features 10 Rutherford engines, including 9 on the first stage and a single vacuum optimized Rutherford engine on the second stage. Rocket Lab successfully flew a recovered Rutherford engine in 2023. Hence, the number is 509 engines rather than 510. Now let's have a look into the distribution of launches made by them from each pads, including today's launch. Just for the background, Rocket Lab operates 2 launch sites comprising a total of 3 pads for the Electron launch vehicle. 2 launch sites, that is the Pad A and Pad B of Launch Complex 1 located in Mahia, New Zealand, and another Launch Complex 2 at Mid-Atlantic Regional Spaceport within the NASA Wallops flight facility in Virginia. So now speaking of the stats, they got 26 orbital launches from Pad A of Launch Complex 1, and 21 orbital launches from Pad B of Launch Complex 1, including one of today's mission launch. To date, they have been there have been 4 orbital launches from Launch Complex 2 in Virginia. So to sum up, they got 47 overall orbital launches from Launch Complex 1 here in Mahia, New Zealand, including today's launch. Moving on to this year's orbital launches, including today's one, the United States is dominating with 89 launches, including this mission. Overall launch comprising a substantial 64.5% of the global total. China follows closely behind, accounting for 23.9% with 33 launches, with recent launch of Long March 3B E on WHG-02 mission for high orbit internet satellite. Now Russia maintains a steady pace with 8 launches, with previous Soyuz 2.1A launch of ISS Progress 88, also known as Progress MS-27, ISS cargo resupply mission on May 30th from Baikonur Cosmodrome, making 5.8% of the pie. We have an upcoming launch of Progress MS-28, another cargo resupply mission on August 15th, which will mark the 181st flight of a Progress. On the other hand, Japan has 4 launches so far, making 2.9% of the pie, with the recent H3-22S launch vehicle on its second launch for this year on Advanced Land Observation. Let me say it once again. Advanced Land Observing Satellite 4 mission, that is ALOS-4 mission on 1st July. Meanwhile, both India and Iran made their participation with 2 launches each, contributing to 1.4% of the global total. Also, it is worth mentioning this year's first successful orbital launch was made by India. We have an upcoming launch of ISRO's SSLV, that is Small Satellite Launch Vehicle Flight 3 mission on August 15th, marking India's 3rd mission of 2024. Although quite a close competition, but United States and China are undeniably dominating the space race this year. And addressing to my viewers, Rocket Lab has already started its stream, and on the right corner of your screen you can see if when they will start the webcast, we will switch to the webcast. So until that time, let's just discuss remaining of the stats. And confusion at 3 a.m. Right now we can't, but we will remember your request, and for the next time we will try to show it during the stream. And really it's quite fascinating, because previously SpaceX used to catch the Fairinghouse with a net on the recovery ships, and here Rocket Lab did recover the boosters aerially with the help of helicopters. So we do have some pictures of that, but would like to show you on the next time. Right now we will be actually running out of the time, so please be here with us. So now we have this pie chart showing 2024 orbital launches by rocket variations, including today's launch. Let's have a look and let me break it down for you. The green slice of the pie, that's the Falcon 9 rocket, the superstar of this year and the real heavy hitter, having the biggest share of the pie with 73 launches, including one from today from Kennedy Space Center on Starlink 10-6 mission, launching 23 Starlink satellites, making up more than half of the whole pie at 52.1% and leading. Next up, we have got the rocketlab's Electron with 9 launches, including one from today, making 6.4% of the pie. With the recent 50th Electron launch on No Time to Lose mission, Rocket Lab has successfully reached its 50th launch faster than any commercially developed rocket in history, now holding the title previously owned by SpaceX Falcon 9. We were supposed to have a sky full of stars, that is another synthetic aperture radar mission, launched earlier on July 21st, but it is now being postponed and no specific date has been mentioned by Rocket Lab yet. Next up, we have Roscosmos Soyuz 2.1A and 2.1B rockets with 7 launches so far this year, which is 5% of the pie. Then we got the China's Long March 2C, that is CZ2C, and Long March 2D, that is CZ2D rockets. The CZ2C, that is Long March 2C, has 4 launches, making 2.9% of the pie. And the CZ2D, that is Long March 2D, has 5 launches with 3.6% of the pie. All the smaller sizes of the pie, but every launch counts. And lastly, we got this pink slice, another bigger slice of the pie labeled Others, which is a mix of different rockets, including Ariane 6, Falcon Heavy, Atlas 5, Delta IV Heavy, Starship launches, Vulcan Centaur, ISRO's GSLV Mark II and PSLV DL, Japan's H3 and H2A, Iran's Simorgh and KM100, Russia's Angara A5, China's Gravity 1, Long March 7A, and others. The names are not exhaustive and the list is long, so I'm not taking all the names. They got 42 launches in total, which is 30% of the pie. So now, as we eagerly await the launch, let's celebrate the achievement and embrace the challenges that Rocket Lab has encountered. So far, Rocket Lab has still not started the stream. So as we wait for the stream to begin, let's have a look at the chat. Actually, we were having some electrical issues, as you might be knowing that it's been a very bad weather going on here at India. So for that, I was postponing the stream with 10 minutes, hoping that the electricity will come back. Although we do have an inverter, but would like to save that power in case the electricity won't be coming back for the whole night. So for that, we got a little late and we are thankful to you that you were there from the very beginning. Also, thanks for sharing the stream on X. And no more, we should be calling it Twitter. It's now X. Don't call it Twitter anymore. Yes, I know it's good evening here, and you never know a person who is watching from where. So I just addressed everyone with good morning as from the New Zealand time, as because this is a launch from New Zealand. That's why I said good morning. Actually, this might be the case, all for one and one for all. But this owl, this has a specific connection with their launches. They didn't just randomly choose this. Would like to say about that. That's Synspective StriX satellite draws its name from owl's scientific name, StriX uralensis. I hope I can pronounce it good enough. And if not, please pardon me. Owl, so let me say more about it. Well, the webcast has begun. Owls have highly developed hearing and vision, allowing them to forage even in total darkness. Being able to see at night, it also has an important feature of SAR satellites as well. The satellite have an extended antenna reminiscent of bird's wing, further underscores this connection to its namesake. So I hope I could make you understand that how they chose owl in case of the mission name.
Nice and early on August the 3rd here in New Zealand, and we're thrilled to be joining you for our 51st mission. What you're looking at right now is a live view of our Electron rocket ready for launch from Mahia, New Zealand, as the countdown to liftoff continues for our mission partners today, Japanese Earth observation company Synspective. Launch is scheduled this morning for 4:39 a.m. local or 16:39 UTC. My name is James Rattray.
And I'm Likita Satursala, and we're joining you from rocketlab Mission Control in Auckland, New Zealand. Launch operations have run smoothly overnight with no blockers across the launch vehicle, launch pad, or payload on board. The weather is looking clear, and the team remains on track for an on-time liftoff in about 17 minutes. The payload onboard Electron today is the latest satellite and constellation being built by Synspective, a Japanese Earth observation company deploying a constellation of Synthetic Aperture Radar, or SAR satellites, designed to produce images that can show millimeter-level changes to the Earth's surface from space. SAR is a type of imagery that uses radar waves to map the Earth's surface. What bounces back to the satellite sensor is used to determine the distance between the sensor and the object and create a map of measurements of that surface.
Rocketlab has been the sole launch provider for Synspective's constellation to date, and this latest mission continues a lasting and trusted partnership to deploy their StriX constellation to low Earth orbit. Here's more from Synspective.
We would like to beg your pardon. We can't play this audio as this might can have some copyright claims. So please bear with us. Although there is no vocals to make you understand about this, it's just an audio like music playing on, so you can just understand from the visuals as well. Also would like where I was left behind, that we were talking about the name, how it is inspired by the owl. So often referred as owl is often referred as a symbol of wisdom, and the owl was also the sacred messenger of Athena, the Greek goddess of wisdom. This association with owls not only reflects the satellite's technical capabilities, but also it plays in the broader legacy of exploration and insight. So I guess confession at 3 a.m. I could somewhat make you to understand how the name is connected with the mission name. We are thankful, and really that makes us inspire more when we hear that our work is somewhat helpful for you. Thanks for your kind words and inspiring words as well. Confession at 3 a.m.
The name for today's mission is Owl for One, One for Owl. A bit of a tongue twister there, which discontinues our streak of naming Synspective missions with an owl theme. That's because Synspective satellites are named StriX, which draws from the scientific name for an owl. Owls have highly developed hearing and vision, allowing them to forage even in total darkness and being able to see at night, very similar to these STAR satellites.
Now, this mission for Synspective was actually brought forward in our schedule of launches on Electron this year, which, when just a few days before launch, the original customer for our 51st mission asked to move to a later launch to complete additional testing for their spacecraft. Now, responding rapidly and being flexible for our customers is nothing new for us, so with rockets at the ready, we were able to leapfrog to Synspective and get them to the pad sooner. Now, flying dedicated means customers have flexibility over the launch schedule so that their satellites aren't left behind if they miss a launch deadline like on traditional rideshare missions. This is our responsive and tailored launch service with Electron at its best, demonstrating a win-win for both our customer, our other customer, and Synspective.
Alright, coming up next will be the go no-go poll for this mission, run from mission control by our launch director, Julia Wimbacher. They will check in with each operator on console for the go no-go decision on whether to proceed towards liftoff, based on the status of each system that they're monitoring. We're looking for all goes from our operators to move forward. Let's pull up the audio channel from mission control now to listen in.
Well, would like to mention that in this year we will have another Synspective launch later.
To all operators, LDN mission code, we are proceeding now with the go-no-go sequence. Stage.
Stages go.
Avionics.
Avionics is go.
GNC.
GNC is go.
Recon.
Beacon is go.
T1.
T1 is go.
GC.
GC is go.
PLS.
PLS is go.
RSO.
RSO is go.
MET.
MET is go.
MM.
MM is go.
And LD-SUB.
LD-SUB is go.
The go-no-go sequence is complete. We are currently T-minus 11 minutes and 21 seconds in counting. We go for the terminal count order sequence at T-minus 10 minutes. From this time, the 3-word hold procedure is in effect.
Would like to welcome, excuse us for that we couldn't welcome you right on time. Welcome, call me Seb, and yes, you are right that StriX is Latin for owl, and as they mentioned also, and I mentioned it previous as well, but here the StriX is coming from owl's scientific name, which I said, and although I'm not sure that whether I'm pronouncing it right enough, that is StriX uralensis. That is the scientific name of an owl. So from that, they derived the name StriX for the satellite. Anyways, but welcome to our channel. Call me Seb. Hopefully you will enjoy the stream. But confession at 3 a.m. I didn't understood what you wanted to mean with that. Smart people look exactly like people that are not smart. Who is smart and who is unsmart over here?
Missions like we're doing again for today's launch, our team has created a custom expanded fairing that encapsulates Synspective's wide-body satellite on Electron. We'll also be performing an advanced mid-mission maneuver with Electron's kick stage that will shield the StriX satellite from the sun and help to reduce radiation exposure ahead of payload deployment.
And we have plenty more missions with Synspective to look forward to after recently signing our largest launch agreement to date with them for another 10 launches. Just a couple of months ago in Tokyo, Japan, our founder and CEO, Sir Peter Beck, met with Synspective's founder and CEO to announce the agreement, which comes on top of 2 other launches for Synspective, one of them today's mission, which had already been booked to launch this year from Launch Complex 1. Now, including the missions we've already completed for the company, that's 16 launches in total that are on the books for Electron and Synspective. With these dedicated launches on Electron, Synspective has control over the launch schedule and the deployment parameters for each satellite, allowing them to build out their constellation on their terms.
And speaking of tailoring things to our customers' needs, you might have noticed the fairing for this mission looks a little different than usual. The bubbles or bumps that you see protruding from the standard fairing are specially designed to accommodate the unique shape and form factor of Synspective's satellite. It's not the first time we've tailored an Electron's fairing to meet customers' needs. If you've been watching us closely, you'll occasionally see extra tall ones, extra pointy ones, and on occasion, slightly bubbled ones like this one. Being able to tailor our fairings to mission-specific requirements opens up the range of spacecraft we can fly. Just another way Electron has changed the game for dedicated small launch.
About the launch control team you are talking about, confusion at 3 a.m. If yes, I think they are smart enough. That's why they are sitting there. And they are indeed the smartest because they are in their hands only everything is being controlled. If you are meaning about the launch control team. But please, if not, then you can say. And as we can see right now, the strong back is reclining here for the Electron. Now the Electron is standalone, standing
Now,
upright.
a huge part of our business these days is more than just launching satellites. It's in building them and the parts they're made of for our customers all over the world. Most recently, our space systems team hit a really exciting project completion. They've completed the build, testing, and integration for 2 satellites headed to Mars for NASA in just a few short months. These twin spacecraft are part of the ESCAPADE mission to Mars, where they'll measure plasma and the magnetic fields around Mars to help scientists learn more about the planet's climate evolution.
We've built these spacecraft for the University of California, Berkeley Space Science Laboratory. So in reference to their college colors, these satellites are named blue and gold, or the twins as our teams like to call them internally. Scientific missions to Mars can sometimes take a decade or more to get from idea to reality to launch, but our team's been able to produce blue and gold in just 3.5 years. Almost every part of satellites have been built at our sites across the world, including the composite structures and propellant tanks, solar panels, star trackers and reaction wheels, RCS system, and satellite radios to communicate home from Mars. We can't wait to see them arrive to Cape Canaveral for launch vehicle integration in August. The countdown to Mars is on.
Now, while missions to Mars require deep expertise, sometimes it's not all about rocket science. And for some of our open roles in rocket and satellite production, it's not all about being a rocket scientist either. As we scale up our facilities and take part in bigger missions, we're looking for people to join the team on our factory floors, helping us to supply the satellite industry and build the rockets that'll take them to space. If you have the drive, willingness to learn, and some translatable skills from other industries, then we want to hear from you. All of our new production team members complete our Rocket Lab Academy and are trained on the ins and outs of our vehicles and systems and processes. There's a place in space for you, or at the very least, in our production facilities to help us get there. So check out our website for some of those open roles in production today.
We're now in the final moments in the countdown to liftoff. Very soon, in T-minus 2 minutes, the rocket's flight computer will take over and run through the final launch preparations and actions. The team will continue loading Electron with liquid oxygen into its first and second stages. At T-minus 1 minute and 30 seconds, when the propellant loading is complete, we should hear a call-out from Mission Control that lock system is in circulation. Soon after, we can expect Electron's first and second stages to be fully pressurized and ready for launch. The clock will continue counting down, and at T-minus 10 seconds, our launch director will begin the countdown to liftoff. Let's hand it over now to Mission Control.
Avionics LD.
Sequence 58 is complete.
Copy, thank you. To all operators, LD and mission code, from now on there should be no red flags on your critical LCCs. Avionics, LD mission code.
LD avionics.
Disable the loom heater and confirm.
Disabled, confirmed.
VCON, LD mission code.
LD VCON.
Lock the auto sequence and confirm.
Locked.
And VCON, please confirm that all expected primary flight computer ASCOs are green.
Confirmed. Green.
To all operators, we are go for auto sequence start at T-minus 2 minutes. LD is go for launch.
So launch director giving the go for launch for today's mission. The 51st Electron launch on Owl for 1 for Owl mission for Synspective Synthetic Aperture Radar. Fifth out of 16 planned launches for Synspective. Now currently we are at T-minus 1 minute and 50 seconds.
All vehicles fully on internal power. AFTS is green, enabled for flight.
The Electron is on internal power as we heard the call out. Now the liquid oxygen tank pressurization is also begun.
Launch load is complete. System is in recirculation.
Stage 1 and stage 2 locks reach flight pressure. We heard that the LOX load is complete as well. At T-minus 57 seconds, the fast purge will be enabled.
Anti-geysering is disabled.
T-minus 55 seconds, stage 2 fuel will reach the flight pressure. T-minus 45 seconds, the water deluge system will be activated. T-minus 30 seconds, the GNC initialization takes place.
Tanks are pressed for flight.
High flow engine purge enabled.
we heard the call out that fuel tank pressurization did occurred and the fast purge is enabled. Now at T minus 30 seconds, the GNC initialization will take place. Then coming up at T minus 20 seconds, the final engine setup will be completed.
And T minus 20 seconds and counting.
At T minus 2 seconds, we will have the first stage ignition as the Rutherford engines ignite.
10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Liftoff.
That roar is quite fascinating. We did had a successful liftoff for Electron.
Stage 1 propulsion nominal.
Stage 1
Our
propulsion
51st
is
Electron
nominal.
rocket is soaring off the pad and on its way to space for Synspective. Electron is quickly coming up on its first mission milestone to pass through the point of maximum aerodynamic pressure against the rocket, otherwise called out as max Q from mission control. We'll listen out for that now.
Max Q will be happening
Sonic, approaching max Q.
at 1 T plus 1 minute and 6 seconds, and we did got a call out that Electron is supersonic. That means that it has reached the Mach
8
1.
VB discharge nominal.
Cleared max Q.
That was the call we were waiting for. Electron has cleared max Q and is continuing nominally on its journey to space. We're now past 18 kilometers in altitude as the rocket reaches speeds of more than 2,300 kilometers an hour. Up next will be 3 actions that take place quickly one after the other. The first event is MECO, which stands for the main engine cutoff. This is when the Rutherford engines on the bottom of Electron slow down before shutting off completely in preparation for the second event, stage separation, which is when the largest section of Electron separates and falls away from Electron's second stage. Soon after that, the Rutherford engine on the second stage lights up and the mission continues, with the third event called out across mission control comms as second stage ignition. We'll be able to watch those actions in real time from the rocket's onboard camera and hear the call out from mission control, which should be coming in shortly.
30 seconds.
So we are at T plus 2 minute and 17 seconds. We will have the MECO at nearly
15
T
seconds
plus
to staging.
2 minutes and 37 seconds, as we heard
Detect mode.
15 seconds away from the stage separation. We will have the MECO at T plus 2 minutes and 37 seconds. That is the main
MECO
engine cutoff.
confirmed.
And the MECO is confirmed,
Stage separation confirmed.
as well as the stage
Stage 2
separation
ignition
is
confirmed.
confirmed. And the stage
There we have it, a successful MECO, stage separation, and second stage engine ignition for Electron and Synspective. Electron is traveling at more than 7,600 kilometers an hour and now at 102 kilometers above Earth. Our next launch event will be the separation of Electron's fairing when the nose cone splits and falls away, exposing Synspective StriX satellite to space for the first time.
right now, the Rutherford engine on the Electron second stage are at full power. Coming up, the next milestone
Fairing
event at
jettison succeeded.
You saw it there yourself
and
and heard
we
it from
got
mission
it.
control. Electron's fairing has separated and we have a nice clear view of Synspective's satellite in space. The mission is continuing nominally so far on its way to its 543 kilometer orbit.
the fairing are being jettisoned successfully at T plus 3 minutes and 24 seconds.
Guidance is nominal.
Coming up, next event will be T plus 6 minutes and 33 seconds. We will have the battery hot swap.
Now, Lakita, you're the structural analyst for this mission. Can you tell us a little bit about what's required for launching into orbit?
Sure. So, in short, our team works on ensuring that the rocket would survive the harsh launch loads. For example, the new custom fairing that we talked about before would change both the structural and dynamic loading on the vehicle. In other words, the force and vibrations the rocket would experience throughout flight, like at max Q. And all the components on the vehicle also need to be tested to these loads. So our job is to define these loads and analyze the strength of the vehicle and components within to make sure they can handle them.
Confusion at 3 am. For that, I guess you should be contacting SpaceX. They launched at the Spaceman now with a car. So maybe they will be launching and you can have a ride on a car that's also in a space. But remember, you have to be in a spacesuit. And I guess that won't be comfortable for you.
We're coming up now on the battery hot swap for the second stage Rutherford engine. This occurs when the engine switches over to a new set of batteries to power its electric pumps once the first pair are almost out of energy. Once the swap is made, the old batteries fall away from Electron, and sometimes we can see these shiny silver packs on the screen as they fall. So let's keep our eyes on the screen and listen in for the call that battery hot swap has occurred.
We are currently 3 minutes 1
Hot swap
second.
successful.
Battery jettison confirmed.
Battery hot swap is successful.
That was a call that battery hot swap is confirmed. For those of you who have seen a few of our mission broadcasts, you will have noticed some new hardware on the second stage, which forms part of our new generation battery system for Rutherford engine. We redesigned the batteries to introduce more resiliency into the system and improve its electrical performance, allowing for an increased payload capacity on Electron.
Stage 2 propulsion holding nominal.
Good call out for stage 2. The propulsion is nominal, and during the
AFTS
last
is saved.
milestone at 60 plus 6 minutes and 33 seconds, that is the battery hot swap, where a pair, that is 2 high voltage batteries, are being jettisoned. Now the rest of the flight will be solely
The mission is
relied
continuing nominally thus far at
on the single high voltage battery. Now coming up at T plus 9 minutes and 3 seconds, we'll have the second engine cutoff, that is SECO on stage 2.
really, really fast. Orbit is basically a constant state of falling. So in order for us to try and combat the force of gravity trying to bring us down, we have to exceed speeds of 27,700 kilometers an hour.
T plus 8 minutes and 20 seconds into the mission, and we're coming up shortly on the second stage's final actions, cutoff of its Rutherford engine, called out as SECO, which is then followed by Electron's kick stage separating off the Synspective's payload. Callouts from the operators in mission control should be heard shortly, so let's listen in.
We are just 10 seconds away from the second engine cutoff, that is SECO on stage 2. 4 seconds later, we will
SECO
have
confirmed.
stage 2 separate from kick stage. And we did got the call out that SECO
Stage
is
reset.
successful.
And there we have SECO confirmed by what you see on your screen and from the operator call out in mission control. The kick stage with Synspective's payload has also successfully separated and is now entering what we call a coast phase. With the kick stage released into an elliptical orbit around Earth, it needs to complete a half lap of Earth before it can be propelled onto a circular path by the kick stage's Curie engine. Once in place on a circular Earth orbit, the kick stage will be ready to release Synspective to its destination in space amongst its constellation.
From Earth to orbit in 9 minutes and 7 seconds. Not bad, really, is it? We'll take a bit of a break on the webcast while that first half lap is completed, but we'll be back with you to take you through payload deployment and the end of the mission in about 45 minutes. So we'll see you back here soon.
So next up we will be having the kick stage Curie engine ignition at T plus 54 minutes and 7 seconds, which is, as you already heard, from now 45 minutes away. And that Curie engine burn will be lasting for approximately 2 minutes and 15 seconds. Shortly after that, at T plus 57 minutes and 12 seconds, we will have the payload deployment for the StriX satellite. So right now they are playing some music, so why not to play some music from our end as well. Well, we have plenty of time, so let's just discuss about Synthetic Aperture Radar, that is the SAR. Actually, every satellite that we build is in the class of artificial satellite, as we know. So the artificial satellites are categorized into 3 main types: communication, positioning, and Earth observation satellites. Moreover, Earth observation satellites are subdivided into optical and synthetic aperture radar types. Among these, we are involved in the development, manufacturing, and operation of the SAR satellites. Synspective satellites, which are classified as Earth observation satellites, observe terrain and the shape of structures. In building a constellation, factors such as number of satellites, their resolution, and latency, including order processing times, are quite crucial. Equally important is the choice of the orbit for deploying satellites, especially when providing data sets from time series analysis and change detection, which are distinctive capabilities of SAR satellites. As I mentioned before about the orbit for today's payload, It will be on a sun synchronous orbit at 543 kilometers from Earth and will be with an inclination of 43 degrees. Traditional large synthetic aperture radar satellites are designed with a focus on maximizing coverage with each individual satellite using a sun synchronous orbit to ensure global reach. This orbit enables them to pass over the same area at consistent local solar times, typically every few days. And here is what that makes the difference between a traditional large synthetic aperture radar satellites with Synspective's small synthetic aperture radar satellites. In case of smaller synthetic aperture radar satellites, it is feasible to develop and launch multiple satellites for the equivalent cost of one large satellite. By deploying these smaller satellites into sun-synchronous orbit, global coverage can be achieved more efficiently. In case of the smaller SAR satellites, which enables consistent monitoring of the same area, which is not possible in case of the larger SAR satellites because it takes some days or maybe a 24 hours of time period to pass over the same area, whereas in case of smaller SAR satellites, like in case of Synspective, we can constantly monitor an area no matter what is the time. And as I mentioned before, today's satellite will be having an inclined orbit. So let me just make you to understand what is the difference between a sun synchronous orbit with an inclined orbit. In case of inclined orbit, the satellite orbits around the equator up to the mid latitudes, enabling focused imaging of low to mid latitude regions, whereas in case of sun synchronous orbit, satellite orbits through the north and south poles, enabling imaging of the entire Earth's surface. The orbital inclination is important in determining the satellite's coverage area. The orbital inclination angle indicates the angle between the satellite's orbit and the Earth's equatorial plane. By choosing a sun-synchronous orbit, which by design is inclined for today's launch, it's possible to focus on densely populated area in low to mid-latitude regions. This also enables the effective capture of the images in high-demand areas. Although I'm not aware of this, but due to some constraints, there are some areas that become invisible caused by the relationship between the satellite's imaging direction, that is the angle, and the land's slope gradient. By utilizing sun-synchronous orbits, it is possible to capture images from all four cardinal directions. That is, in case of today's payload, we can have the images from all the four directions: east, west, south and north, enabling the selection of imaging combinations that effectively avoid these invisible areas. Synspective is planning on building a constellation that combine multiple orbits in the near future. And during preparing this stats and everything about today's launch, somewhere I just read that they will be making this constellation for synthetic aperture radar for 30 small SAR satellites, but this is in the planning stage, and I guess for that only right now Synspective has signed the contract with Rocket Labs for 16 launches. And as we heard in the webcast that Rocket Lab is the sole launch provider for the Synspective since its very inception of building the Synspective constellation. Although previously Synspective Alpha and Synspective Beta was launched by Electron only, and those two launches were prototype launches for their constellation, and hopefully Synspective will be collecting data from those prototypes to build their constellation more efficiently. Just let me have the information for you guys because I am a little confused about this, that which one is operational between the StriX Alpha and StriX Beta satellite. Out of them, on one is non-operational right now. Well, as I was mentioning that the two prototype satellites launched, that is the StriX Alpha and Beta in 2020 and 2022. Out of them, StriX Alpha is now currently not operational, whereas the StriX Beta is operational, and it will be operational up to the year 2032. It was launched back in 2022, whereas StriX Alpha, which was launched in 2020 and it got non-operational in this year, that is 2024. While discussing the payload details, I just mistakenly overlooked one thing to mention, that about the antenna for today's payload, that is StriX is equipped with a deployable parallel plate slot array antennas, which I mentioned, but let me break it down more for you. That it is also composed of 7 independent panels. Before entering orbit, it measures approximately 80 centimeters on each side, forming a cube. After being placed into orbit, the folded panels then deploy in outer space. The design of the antenna, especially the radio emission slots on its surface and its waveguides, requires detailed calculation related to the radio wave phase. However, once the design is set, the manufacturing and the inspection process are simplified, and this is the quality of Synspective StriX satellite, that not only does it have fewer components compared to other traditional synthetic aperture radar satellites, but it is also lightweight and is less reliant on electronic devices and boosts notable structural strength. While speaking of less electronic devices on the StriX satellites, I would like to mention what does the instruments are on board the StriX satellites. The RF peak power, which is selected to 1 kilowatt, that is realized by G and A solid state amplifiers instead of vacuum tube, that is the TWTAS. It consists of a cherubed transmitting signal which is amplified in 6 G and GAN HEMT 200 and 200 watt amplifier modules to be considered in a waveguide resonator. I know these are a little bit complicated to understand, but I'm just mentioning for those who can understand these things. Else you can just overlook this. This is not at all such important to understand. And moreover, on duty to ratio is 25% to increase the average power. The SAR satellite also consists of an electronics unit that is acronymed as SELU, which handles transmitting signal generation, receiving signal processing, frequency conversion, and analog to digital conversion for SAR sensors. This SAR electronic unit for small satellites is developed based on an airborne SAR instrument. The chirp bandwidth is 300 MHz for 1 meter ground resolution. The received signal is converted to digital signal of 8-bit multiplied by 720 M samples per second, and the data compression rate is about 50%. The receiving duty cycle is about 50% to acquire reasonable signal to noise ratio, and after time stretching process, the average data rate is 1.5 gigabytes per second. In the SAR observation mode, this is another mode in which the SAR satellites can operate. So speaking of that the SAR observation mode, the average data rate will be 1.5 gigabyte per second and will be transferred to MDR, that is the mission data recorder, through a serial rapid IO interface. Here the rapid IO, as the name suggests, rapid means frequent and IO is input output, and the MDR consists of a commercial 16 NAND flash memory devices, and the total memory capacity is 768 GB. So this is the total memory on board a Synspective SAR satellite. Total dose tolerance of NAND devices is confirmed by CO60 irradiation test, and single event offset errors are corrected by standard error correction code for commercial NAND devices. A commercial FPGA, that is the field programmable gate array device, is also utilized for high speed data flow and standard powerful error correction code. Special cares are paid to thermal heat path and thermal stress of the ball bird array, that is the BGA packaging, and in the downlink communication mode the stored data are transferred to high data rate X band transmitter, that is the XTX, which has dual polarization RHCP or LHCP channels to increase its downlink capacity. The stored data are switched to two channels and they are transferred to XTX, that is the X band transmitter, through Xilinx, I hope I can pronounce it right, Aurora data interface. The data rate between the MDR and the X band transmitter, that is the XTX, is 2 gigabytes per second per one channel, and the total data rate overall is 4 gigabyte per second. Confession at 3 a.m. I didn't knew that my mom is here also watching the stream. Thanks for reminding me to drink water. We are currently less than 3 minutes away from the kick stage Curie engine ignition. At T plus 54 minutes and 7 seconds, the kick stage Curie engine will ignite, and that Curie engine burn will last for approximately 2 minutes and 15 seconds. Shortly after, at T plus 57 minutes and 12 seconds, we will have the payload deployment completion for the StriX satellites for today's mission. Yes, confession at 3 am, Mama Ratsa. Remember? Who else says about drinking water in a live chat? Well, yes, indeed, this part of the stream is boring, but this gives you a little bit of time to have your things to be done in between and coming back, as I did, and I didn't ran away. And right now, sorry for that I can't show you the pictures of the electron booster being catched by helicopters, because we have to first check it whether we can show it on the stream or not, although we will try hard to make it available for you in the next stream of Rocket Labs, because as you know, who knows, we can get a copyright strike for that only. So it has to be a public domain image which we can show to you. But which images I am having right now, I'm not aware that whether they are available in public domain or not. So first I have to check that, then only I can show you. And even not, like, even if those images are not in public domain which I am having with me, I will try somehow to manage something to give you at least the idea how it is, the operation is being done. So we are now getting close for the Curie engine ignition. We are just less than 30 seconds away from that. Hopefully they will come back and talk about it.
Hello and welcome back to the webcast of Rocket Lab's 51st Electron launch, a dedicated mission for Japanese Earth imaging company Synspective. Less than an hour ago, Electron launched off the pad at Launch Complex 1 in New Zealand at 4:39 a.m. local time. From there, the rocket has made its way cleanly through the usual launch milestones like max Q, first stage main engine cutoff, state separation and ignition on second stage engine, followed by SECO and state separation again, but between Electron's second stage and the kick stage that's carrying the StriX payload.
That kick stage was released to space on an elliptical trajectory, and it needs to be on a circular path around Earth to accurately deploy Synspective satellites. Now, the kick stage's 3D printed little Curie engine was ignited a few minutes ago to circularize this mission's trajectory. To keep the mission on track, soon that engine will shut down to allow the Synspective satellite to be deployed to orbit. Coming up soon will be Curie engine cutoff and payload separation for the StriX satellite from the kick stage. So let's turn up mission control comms and listen in for those confirmations.
The payload deployment for the StriX satellite will be happening at T plus 57 minutes and
Curie
12
engine
seconds.
cutoff confirmed.
And
Target deployment orbit achieved.
we did got the call out for the Curie engine cutoff.
A successful Curie engine shutdown for the kick stage. Only a few more seconds to go now until it's in position to deploy Synspective satellite to orbit. Let's watch the simulation of what that payload deployment will look like.
Right now you can see how the payload is being attached with the kick stage. And here we go, we did got the payload being separated from the kick stage. Now it is being deployed in its intended orbit.
And our mission is now complete. Welcome back to Space Synspective. It's great to have partnered with you again for the latest deployment in your constellation. All the best for your satellite commissioning starting now.
Congratulations to the Rocket Lab team on mission number 51, just a few short weeks after our golden milestone. That's 9 Electron launches for the year now, with our 10th coming up very, very soon, so make sure you keep an eye on Rocket Lab's Facebook, Twitter and Instagram pages, along with our website for more information on our next mission. Until then, thank you so much for joining us. This is Rocket Lab Mission Control, signing off.
So here we have it, the kick stage has successfully deployed the Synspective StriX satellite. Today's launch marked 51st overall launch of an orbital class rocket, that's Rocket Lab's Electron, and this launch marks the 9th launch of Rocket Lab this year. With that, we will wrap up our coverage for now. Be sure to check out our social media, especially on X, for updates regarding any launch and also space updates. And we would like to thank all of you joining us with today's launch. We hope you all enjoyed the stream. Once again, thanks for joining us, showing your such patience, love and understanding, staying till the end. We are glad to have you all here with us. This is AstroYonder Live and me, Dipta, signing off for now, and we will see you next time.